Hi everyone, I'm Ajay. I'm a research scientist at NVIDIA, and today I'll talk about how we can remove the barriers to simulation adoption with automated environment construction and synthetic data generation. We've recently been seeing a ton of amazing robot manipulation videos and content out there, large-scale generalist robot policies capable of doing impressive fine-grained and multi-step manipulation are becoming more and more prevalent. If you just watch these videos, you might think that we've already solved robotics. But, these results are very promising, but there are some key challenges that are being hidden here. First, getting training data for these policies is actually really, really hard. It involves a ton of human effort. This example here is from Gemini Robotics. This operator teleoperates these arms to collect training data. There are thousands of hours of data like this. And we're seeing fast progress right now, but we need better data sources. And second, evaluating these policies is a painful and time-consuming process. Normal real-world policy evaluation is bad, but when you've got multitask and multi-embodiment policies, it's a lot worse. For each model, you need to run multiple rollouts on each task and each robot, and this is just a single model checkpoint. The auto eval paper gives some concrete numbers for what it took to benchmark OpenVLA. It required over 2,500 rollouts across multiple robot setups and institutions with more than 100 hours of human effort. And the situation is actually even worse than this. TRI ran a careful study of multitask policies using 1,800 real-world rollouts. And even with 50 rollouts per task, policy, and condition, they found the statistical significance of comparisons can be limited. Even careful hardware evaluation is noisy. With 50 real-world rollouts, success rate uncertainty is still often 20 to 30 percentage points wide. And that means that small policy improvements can disappear inside evaluation noise. Long horizon tasks like apple cutting can take 3 minutes per successful rollout, which means 2.5 hours of robot rollout time for 50 rollouts. And that doesn't even include the time it takes for a human to reset each scene every time. So then, are we doomed? I don't think so. I think we really just need to turn to using simulation more heavily. Simulation can greatly accelerate policy deployment. First, it can support large-scale autonomous data generation methods. These data generation methods can be applied to a diverse supply of simulation environments, since simulation can support procedural generation of environments and assets. And second, simulation allows for automated policy evaluations. We can reliably evaluate policies in a reproducible manner across large numbers of benchmark tasks with a high number of evaluations. So if simulation is so great, why don't more people use it? Well, there are some substantial barriers that prevent widespread simulation adoption. First, the traditional pipeline of manually creating and tuning simulation simply doesn't scale. Traditionally, a human painstakingly engineers simulation scenes and tasks. Then they carefully tune the visuals and physics to align as best as they can with the real world. Creating a single simulation task this way can take hours, if not days. The scope of what simulation can handle can also be significantly limited. We know how to simulate clean scenes with rigid body interactions pretty well, but the real world is so much messier. This is a typical real world scene, cluttered and disorganized, consisting of deformables like towels, cables, with reflective and transparent objects. Simulating this kind of scene is not easy. So in this talk, I'm going to discuss how we can start removing some of these barriers to simulation adoption. I'll mainly focus on our new real-to-sim system called SimFoundry, which automatically generates simulation environments from real-world inputs. This makes it possible to create simulation with very little engineering burden. The generated scenes are grounded in the real world, substantially reducing the sim-to-real gap and making the simulation scenes immediately useful for real-world robot policy deployment. Finally, I'll briefly highlight a couple other research efforts where we make progress on increasing the scope of simulation to challenging applications like deformable object manipulation and humanoid loco manipulation. Let's start talking about SimFoundry. SimFoundry starts with a real-world video, and it creates a simulation-ready digital twin, like shown above. SimFoundry doesn't just create digital twins, though. It also constructs digital cousins, which maintain the semantic and geometric affordances of the scene, but provide meaningful sources of variation. The colors and textures for many of the fruits change, for example, providing visual variation, but there are also geometric variations. The basket changes substantially into one with much wider handles, and the grapes are much more compact, for example, and so on. In this way, SimFoundry can create natural and diverse digital cousins. SimFoundry also works seamlessly for challenging cluttered real-world scenes like this one shown above. Here's the digital twin that SimFoundry created. It manages to handle occlusions pretty well. And here's a digital cousin. Here's another real-world example shown above. And this is the digital twin that SimFoundry created. It looks okay, but if you're a chocolate fan like me, maybe you want your scene objects to be a little bit more chocolatey. So here's a cousin. It does just that with the ice cream cone, the cookie, and the pretzel. Now here's an outdoor scene and the twin that SimFoundry created. And then here's one of the digital cousins it created as well. Another example is a typical table for some, quick and easy coffee. And this is what SimFoundry reconstructs in the digital twin. And the cousin with different geometries for most of the objects. This is one of my favorite examples because, there's just so much clutter on this table and it kind of looks like, typical workspaces. And here's the reconstructed twin. You can see it captured most of the details, right? And here's a digital cousin, with many of the objects changed geometrically and visually. Now here's another particularly challenging scene with the wooden spoon on a cup, some tongs in a bowl, and some condiment containers. But SimFoundry still manages to handle it. Here's a twin. And the cousin as well. The cousin has many meaningful variations that I wanted to point out here. So for example, the tongs have red handles, the bottle changes shape and becomes narrower and taller, the cup shrunk while the containers got larger, and these size variations aren't just, uniform scalings, they're actually meaningful. And the bowl changes to have a much more rounded top and a nice texture around the rim. SimFoundry also handles scenes with articulated objects. So here are 3 example objects that are generated by SimFoundry. So this is an overview of the type of digital cousins that SimFoundry generates. Thus far, I showed you object cousins, where the objects change in different ways, but it also supports scene cousins, which rearrange the scene in meaningful ways, and task cousins, where new tasks can be proposed for a robot to perform. Now that I've shown you some of the cool scenes that SimFoundry can produce, let's talk about what you can do with it. There are 2 key real-world applications we focus on. The first is real-to-sim policy evaluation. Here we can start with some candidate real-world generalist policies and a real-world scene we want to evaluate them in. We reconstruct the scene with SimFoundry and then evaluate the policies there, producing ranked policies without manual human evaluation effort. And the second is sim-to-real policy training. Here we can train policies on synthetic data from SimFoundry digital twins and cousins, and then deploy the policies directly in the real world. Let's first go over some results for policy evaluation. SimFoundry can accurately evaluate off-the-shelf generalist policies. Here we take PIO5 from physical intelligence and deploy it with no fine-tuning directly in the real world and in SimFoundry simulation. All the success rates between simulation and the real world are pretty close for all 3 of these tasks. So SimFoundry can provide a great place to just drop in policies and evaluate them, and the results actually mean something. Evaluation results can correlate for more challenging scenarios too. We ended up having to post-train our VLAs to get decent performance on these 2 tasks, the store marker and put away trash task, both of which involve articulated object manipulation. In this case, while the absolute success rates in sim and real may not match, policy rankings are preserved well. The best policy in sim is also the best one in real, and the second best matches 2, and so on. Here's a more quantitative assessment of SimFoundry for policy evaluation. We take several different model types and evaluate them on different tasks. For each policy, we plot its sim success rate against its real success rate. In a perfect world, the results would lie on the y equals x line, where sim success equals real success. While we don't quite hit that, the correlation is still very good. The Pearson coefficient is 0.9. This is across 5 different policy types and 6 tasks, with policies that are out of the box and ones that are fine-tuned as well. SimFoundry compares favorably to some alternatives too. Here we compare to Polaris, which is a state-of-the-art method for real-to-sim policy evaluation. We reconstruct the same scenes and tasks using both SimFoundry and Polaris. You can see the quality above. Notably, SimFoundry is also more feature-rich than Polaris. It supports articulated objects, automatic scene reconstruction, and sim-to-real training. We compared both methods across 5 tasks and 5 policies. Each task was reconstructed in Sim using both SimFoundry and Polaris, and then we evaluate each policy in each simulation environment and in the real world, and plot the success rates on the left. You can see that the simulation and real-world success rates for SimFoundry, shown in green, are much more correlated than those for Polaris, which are shown in orange. Quantitatively, the Pearson correlation coefficient for SimFoundry is much higher, 0.85 versus 0.39, and the mean maximum rank violation is much lower, meaning that policy rankings in SimFoundry are more correlated to the real world. So I've shown you how SimFoundry can be useful for policy evaluation. Now let's talk about the second application, sim-to-real policy training. Data from SimFoundry's simulation allows policies to zero-shot transfer to the real world. Here we show results on the stack dishware task on 2 different embodiments. You can see the simulation evaluations, and now you can see these are the real-world evaluations. And SimFoundry digital cousins also allow for policies to generalize to new real-world objects. These are completely unseen. We didn't reconstruct them. We didn't do anything with them, right? So this kind of thing is made possible by SimFoundry's real-to-sim-to-real synthetic data generation workflow. We start with a real-world scene, and then we reconstruct the digital twin. And then we generate some digital cousins. Then we run it through some synthetic data generation tools. Here we use MimicGen, which is some of our prior work. And then we train a policy from the generated data and deploy it directly in the real world. Here's a more specific look at how policies can generalize to new unseen real-world objects. The left panel shows the reconstructed twin drawer and some cousins, and then the policy is evaluated on a brand new drawer in the real world. Here's some more results on our bimanual YAM arms. Quantitatively, we see a tangible benefit to using digital cousins during the policy training process, compared to only using the twin. And this means that policy generalization comes from the training on the cousins. The policy training results I showed so far were zero-shot, so they were trained only on SimFoundry data and then deployed on the real world. But if we combine SimFoundry's sim data with a little bit of real-world data, we can do even better. On these 3 droid tasks, you can see the zero-shot performance in blue, the real-only performance in green, and then the results of co-training on sim and real data in red. We see significant improvements in co-training over just using purely sim or purely real data. As I mentioned before, SimFoundry can generate new tasks in the form of task cousins. We can take a cluttered scene and then reconstruct it in SimFoundry. Then we can feed the task along with a prompt and some constraints to a VLM to give us task proposals and goal conditions. And this can help us spin up generated tasks in simulation. Next, we can generate large-scale multitask synthetic data for these simulation tasks. And again, this uses MimicGen. It uses the same pipeline that I showed you guys before. So with this, we get a large amount of multitask synthetic simulation data directly in SimFoundry. And then we can fine-tune VLAs on that generated data and then transfer to the real world. So we saw that this synthetic data can improve multitask performance from 28% to 46%. across 13 tasks that were generated in simulation and then evaluated in the real world. And then we even saw that we can go from, a policy that doesn't work to a 29% success rate on 7 brand new held out tasks that were unseen even in simulation. So this really can facilitate policy generalization. So let's dive in briefly into how SimFoundry works. This is an overview of some of the core pieces of SimFoundry. At high level, it consists of real-world extraction, a digital twin reconstruction step, and a pipeline for generating digital cousins. Our first step is to extract knowledge from the real-world scene that can help us reconstruct it. We first ask an AI agent to tell us what objects are in the scene, and then select the object that is least occluded. We then pass this object through multiple foundation models to effectively remove it from the scene. We do this by extracting the object segmentation mask and generating an in-painted image and depth map without the object. We then repeat this process iteratively, querying foundation models in sequence to extract individual foregrounds from the scene. And you'll see this process continues to occur until there are no more detected foreground objects in the scene. So here, one by one, we're taking the objects and we're removing them from the scene, and then we're getting their masks. Once we have all of our extracted objects, we can then generate 3D meshes for them. For each object, we can first upsample its low-resolution raw segmentation mask using an image editing model like NanoBanana, and then pass it through an image to 3D generation model to produce generated meshes. The process for articulated objects is a little bit more involved. We first leverage 3D segmentation models to convert the object's original mesh into multiple parts. And then we leverage models such as GPT to annotate the proper joint configuration to combine all the segmented parts, ultimately producing a functional articulated multi-body object. We then make all our assets sim-ready by querying a VLM to annotate relevant physical properties such as mass and friction, and then we can fit its pose and scale to the extracted scene point cloud. Finally, we take our background video to construct a 3D Gaussian splat representation. And then we can compose the final scene by spawning all the objects and then depenetrating them to ensure physical stability in the scene. Next, I'll show you how we can generate object cousins to give us natural geometric variation in our scenes. If we want to generate cousins for a specific object, we can simply take the original upsampled object, query an image editing model to modify the original image, and then pass that modified image through the mesh generator to generate corresponding cousin assets, which can then be hot swapped directly into the scene. Here you can see the scissors, different versions of the scissors. So one of the great things about SimFoundry is that it's completely modular. It leverages off-the-shelf models at each step of the pipeline. So that means that as perception, reconstruction, and generation methods improve, models can be swapped right in. For example, we can swap in different models for 2D to 3D mesh generation, or different VLM models for making image perturbations in the object cousins generation pipeline. So we benchmarked SimFoundry reconstruction fidelity across a range of scenes with different levels of fidelity. The easy scenes have objects that in tighter spacings and more challenging configurations. Sorry, the easy scenes are more spread out, right? All the objects are kind of spread out on the table, and the medium scenes have tighter spacing. And then the hard scenes have some significant overlap between the objects, and it causes some significant occlusions. And we see that SimFoundry outperforms SAM3D when applied zero shot to these kinds of scenes. And with minutes of human interaction, SimFoundry fidelity can go even higher. How do users improve fidelity? Well, users can apply light edits to object sizes and positions through an intuitive GUI, and some examples are shown in the videos here. So, our work is not alone. There's been a ton of really great research in this space, and that's what makes this workshop so timely and relevant. And I wanted to briefly highlight what makes SimFoundry special. This table shows a few selected recent works, And you can see that SimFoundry is the most feature complete here, showing demonstrated use for both sim-to-real training and real-to-sim policy evaluation, supporting automated scene construction and articulated objects, having experiments across multiple embodiments, supporting asset and digital cousin generation, and also reconstructing backgrounds. All right, so I covered SimFoundry, which allows us to automate the construction of grounded simulation environments, making them directly useful for robot learning applications. And I wanted to very briefly highlight a couple projects where we try to increase the scope of what we can do with simulation. Let's first start with deformable manipulation. This is soft mimicgen, a data generation system we developed for deformable manipulation. We start with a small number of human demos, in this example, just 3, and then soft mimicgen expands these into a large set of new demonstrations, enabling scalable data generation. It can generate data for novel object variations. For example, starting from a single towel demonstration, it can generate data for towels of different sizes, shapes, and colors. And it works for a wide range of deformable manipulation tasks. These tasks include cloths, ropes, bags, cables, and plush toys across single and bimanual arms and humanoids. We trained agents from scratch on soft mimicgen data and deployed them zero-shot in the real world. And it turns out with a little bit of real-world data, we can get even better results. Here you can see that results improve from 63% with just simulation data to 93% using a small number of real-world demonstrations to supplement. So to get these sim-to-real results, we actually leveraged our point bridge work, which is an easy way to transfer agents from sim to real using a unified point-based representation. It works really well for both rigid bodies and deformables, and it's super easy to set up and use. Soft mimicgen generates high-quality data sets that result in performant policies via simple behavioral cloning. Here you can see some of the policy rollouts. This work was led by Masood, and it's here at ICRA actually, so catch it on Wednesday. So finally, I also wanted to briefly highlight our effort on humanoid loco manipulation. So this here is humanoid mimicgen. It's a synthetic data generation platform for humanoid loco manipulation. So here, one demonstration becomes 1,000, right? And this is for the setting of humanoid loco manipulation, where collecting data is just so much more complicated than static manipulation. Synthetic humanoid mimicgen data helps train real-world policies. Here you can see 4 of the real-world agents we've trained on a mixture of simulation, synthetic data, and real-world data. For example, on this box-to-cart task, the synthetic data improved success by 25% compared to just using real-world only data. Humanoid mimicgen trains high-performing VLA policies. Here you can see on this 9-task benchmark that we introduced in the paper, we've trained pretty high-performing agents here. This work was led by Kevin, Kaylin, and myself, and you can also see it in a couple of the workshops. Okay, let's recap what I talked about. I discussed how SimFoundry enables automated simulation generation. It generates digital twins and diverse digital cousins of real-world scenes, and the strong real-world correspondence enables both evaluation and training applications. And I also discussed some promising signs that simulation can apply to real-world scenarios like cluttered scenes, deformable objects, and human workspaces. And I think that SimFoundry really only scratched the surface. Simulation design will get even easier with coding agents. The future is really bright for simulation. So lastly, come see the works I mentioned at ICRA. You can come to the workshop poster session to chat about SimFoundry, and to the main conference to chat about soft mimicgen. And humanoid mimicgen and Point Bridge will both be at the SDRL workshop today and the Beyond Teleop workshop on Friday. The work I covered was made possible by so many amazing, talented people, and I'm really proud of the team and the work we've done. And yeah, I think I'm happy to take questions now, if there's time.
Yeah, thank you for the wonderful talk. I have a very detailed question about the sync-foundry pipeline. I noticed that you said after you register the object into the sync, you do depenetrating to make it a physically possible sync. Could you be more detailed about that? Because I also tried a bunch of root-to-sync pipelines and I found that generating a physically possible sync is very difficult, and I'm very curious how you do the so-called depenetrating and stabilization.
Yeah, that's a great question. For full details, you can see the workshop paper, but essentially what we do is we load the scene in another simulation like PyBullet, and then we run some iterations in there until the objects are not overlapping anymore. So they settle in the scene. And then with those updated poses, that's how we're able to.
I see. So does that mean you kind of inject very large damping in your simulation and try to let the simulation itself naturally resolve it instead of like, say, adjusting a pose or pulling the shapes by yourself? Just throw everything to the simulator and let it just resolve it by itself.
Well, if you directly let the simulator resolve the penetration, sometimes it can explode, right? So I think we've been looking at a number of different approaches here for the depenetration. I wouldn't say that one approach is definitely like the best one. And I think, there's always opportunity in future work to improve this because even our physics parameters are coming directly from a VLN, right? So there's opportunities to actually do this in a more iterative way, for example, right? For this work, what we did is we pipelined off-the-shelf components together in a good way, such that, for different modules, we can improve how they work in the future.
I see.
Yeah.
Thank you for that.
Also, maybe one more question from our side. So you were experimenting with those state-of-the-art technologies, and it would be interesting to know your opinion about maybe for the next upcoming year. What do you think will be an emerging technology that will be main topic of new submissions in next conferences?
Yeah, that's a great question. It's always hard to speculate, but I think one of my last slides was about coding agents, and I really do believe that's the future for simulation. I think with a lot of these kinds of things where, writing code can be automated and the evaluation can be automated, that's something that is very tough to do when you're doing this directly in the real world. But that's what makes simulation so compelling. Simulation at its core is code, right? So that's something that I think if you can close a loop using simulation and you can have simulation be a good proxy for the real world, that's also why we really emphasize in our SimFoundry work, everything is coming grounded from the real world, right? That's what makes simulation useful. So yeah, I guess a combination of like more automated workflows that can use simulation as the major workhorse for enabling research.
Yeah, thanks for the talk. Actually, I was curious about the notion of the central maybe extension behind SimFoundry and differentiating between, for example, digital twins and digital cousins, right? So the paper introduces both. And looking ahead, do you think that these are fundamentally different requirements or kind of single environment, environment generation pipelines simultaneously optimized for both evaluation fidelity as well as diversity of the?
That's a really good question. I actually think that both can be optimized for it. Right now, what I see is kind of like a split where there are people working on fundamentally real to sim, which is more of a reconstruction problem, and then more of a bottom-up simulation generation where people bottom-up generate assets and scenes, right, using LLMs and VLMs and try to promote diversity, right? What we really need is, just like you said, we need these ends to meet, right? So one way to do that, I really think, is like scalable real to sim, right? SimFoundry is kind of just like an initial step in that direction. That's what motivates digital cousins. You take something that's grounded in the real world, but then you spawn variations of it, right? That way the variations are coming from something that you know is a physically accurate object, right? So we need something that meets in the middle, that can match the scalability and diversity of bottom-up generation with the, grounded robotics applications of real to sim kind of pipelines.